So let's talk a little bit about a word you might have heard, and that is ion. Let's talk about what it is, and then we'll talk about trends in the periodic table on I guess, how hard it is to make something an ion, in particular, how hard it is to make something a positive ion. So an ion is just an atom or a molecule that has charge. And it'll have charge if the protons are not equal to the electrons. Neutrons are obviously also a constituent of atoms, but neutrons are neutral. What you're going to get your charge from are your protons or your electrons. So you're going to have a net charge if your number of protons, and this is for an atom or a molecule. A molecule is just a bunch of atoms bonded together. If the number of protons does not equal the number of electrons. And you can have positive ions if the protons are more than the number of electrons. Protons are positive, electrons are negative. And you can have negative ions if the number of electrons are greater than the number of protons. For example, if you just had hydrogen in its neutral state has one proton and one electron. But if you were to take one of those electrons away, then hydrogen would have a positive charge, and essentially it would just be, in its most common isotope, it would just be a proton by itself. And so when we talk about a positive ion like this, where our protons are more than our electrons, the number of protons are more than the number of electrons, we call these cations. Cations. Cation, once again, just another word for positive ion. Likewise, we can have negative ions. So say, for example, fluorine. So fluorine gains an electron. It's going to have a net negative charge. It's going to have a charge of -1. And a negative ion we call an anion. And the way that I remember this is, A kind of means the opposite or the negation of something. So this is a negative ion where we're negating, you could somehow think we are negating the ion. So with that out of the way, let's think about how hard it will be to ionize different elements in the periodic table, in particular how hard it is to turn them into cations. And to think about that, we'll introduce an idea called ionization energy. Ionization energy. And this is defined as the energy required to remove an electron. So it could have even been called cationization energy, because it's the energy required to remove an electron and make the overall atom more positive. So let's think about the trends. And we already have a little bit of background on the different groups of the periodic table. So for example, if we were to focus on, especially, we could look at group 1. And we've already talked about hydrogen's a bit of a special case in group 1, but if we look at everything below hydrogen, if we look at the alkali metals here, we've already talked about the fact that these are very willing to lose an electron. Why? Because if they lose an electron, they get to the electron configuration of the noble gas before it. So if lithium loses an electron, then it has an outer shell electron configuration of helium. It has 2 outer electrons. And that's kind of, we typically talk about the octet rule, but if we're talking about characters like lithium or helium, they're happy with 2, because you can only put 2 electrons in that first shell. But all the rest of them, sodium, potassium, etc., if you take an electron away from them, then their outermost shell, well, all of them, their outermost shell, they're going to have the electron configuration of the noble gas before it. And for sodium on down, that outer shell is going to have that perfect 8. Lithium, if you remove an electron, it would get to helium. It will have 2 electrons in its outer shell. So you could imagine that the ionization energy right over here, the energy the energy required to remove electrons from your alkali metals is very low. So let me just write down. So when I say low, I'm talking about low ionization energy. Low. Now what happens as we move to the right of the periodic table? In fact, let's go all the way to the right on the periodic table. Well, if we go here to the noble gases we've already talked about. They're very, very, very stable. They don't want they don't want their electron configurations messed with. So it would be very hard. I mean, neon on down has their 8 electrons, that kind of octet rule. Helium has 2, which is full for the first shell. And so it's very hard to remove an electron from here. And so it has a very high ionization energy. Low energy, easy to remove electrons, or especially the first electron. And then here you have a high ionization energy. You have trouble seeing that H. So this is high ionization energy. And that's the general trend across the periodic table. As you go from left to right, you go from low ionization energy to high ionization energy. Now what about trends up and down the periodic table? Well, within any group, if we look at the alkali metals right over here, if we're down at the bottom, if we're looking at say cesium right over here, that electron in the 1, 2, 3, 4, 5, 6 in the 6th shell, that's going to be further from that 1 electron that lithium has in its 2nd shell. So it's going to be further away. It's not going to be as closely bound to the nucleus, I guess you could say. So this is going to be even that 1 electron is going to be even easier to remove than the 1 electron in the outermost shell of lithium. So this one has even lower. And that's even going to be true of the noble gases out here. That xenon, that its electrons in its outermost shell, even though it has 8 valence electrons, they're further away from the nucleus. And so they're the energy required to remove them is still going to be high, but it's going to be lower than the energy from say, neon or helium. So this is low. So once again, ionization energy, low to high as we go from left to right, and low to high as we go from bottom to top. Or we could say a general trend that if we go from the bottom left to the top right, we go from low ionization energy, very easy to remove an electron from these characters right over here, to high ionization energy. Very hard to remove an electron from these characters over here. And you could see this in a trend of actual measured ionization energies. And I like to see charts like this because it kind of shows you where the periodic table came from. When people notice these kind of periodic trends, it's like, hey, it looks like there's some common patterns here. But on this one in particular, we see on this axis, we have ionization energy in electron volts. It's literally this is units of energy. You can convert it to joules if you like. And over here, we're increasing the atomic number. So we're starting with hydrogen, then we go to helium, and then we go from hydrogen to helium to lithium. And let me show you what's happening right over here. So you go to hydrogen to helium. So helium here is very stable, so it's very hard to remove an electron. And then you go to lithium. Lithium, as we said, this is an alkali metal. You remove an electron, it gets to a stable state, so it takes very low energy to remove that electron. And then as we go from left to right in the periodic table, as we go from alkali metal to noble gases, we see that the ionization energy increases. And there are these little dips here, which you could think about why these or theorize why these dips are occurring. But you see this general trend as we go from alkali metals to noble gases, alkali metals to noble gases, alkali metals to noble gases. Now, one thing you might be saying is, hey, look, you had from here to here, that's the same distance as here to here, but now we have a larger distance here. What's going on here? Well, we have to remember, now we have all of our D block elements. So now, once we get over here, we're now adding all of the D block elements, like you'd say in the 4th period. And so we have those added here. So you have D block elements, and then here you have your F and D block elements. And so you see the general trend that your alkali metals, very low ionization energy, your noble gases, very high ionization energy. But as the atoms get larger and larger, the ionization energy goes lower and lower. And something like radon, which even though it's a noble gas, its ionization energy, because those outermost electrons are further away from the nucleus, or they're quite far away from the nucleus, that its ionization energy is actually less than that of hydrogen. Anyway, hopefully you found that interesting.